Today, I want to discuss what a matrix is and how we can use a matrix to solve a system of equations, or one of the ways. So, before we go into some of these processes, let's go over some vocabulary. First off, what is a matrix? A matrix is a rectangular array of real numbers. So, an example of a matrix is listed right over here. And every matrix has what we call an order, which is simply a way of describing the dimensions of the matrix. And it always goes the rows by the number of columns. So the number of rows that we have, so for example, in this matrix that I have listed here, we have 2 rows and we have 3 columns, right? Remember, think of always columns going vertically, like holding up a building. So it's a 2 by 3 matrix. That's how we describe it. It's always the number of rows by the number of columns. And within each matrix, we have a bunch of values in which we call entries. And each entry has a number assigned to it so we can identify where that entry is. So this value here, this entry is A sub 1, 1, meaning it's the entry in the first row of the first column. And this one right over here, A sub 1, 2, would be the entry in the first row of the second column. So here we can just go ahead and fill out the rest of these. We would say this is A sub 2, 2. This would be A sub 3, 1, A sub 3, 2, which would, again, this value here indicates that it's in the third row of the second column. Well, what is the order of this matrix? This would be a 3 by 2. A row matrix is a matrix that simply has just one row in it. So this would be a 1 by 3 because it has one row and 3 columns. And a column matrix only has, and there's a typo there, sorry, that should say column. This should be only one column. So this would be a 3 by 1. Now, a square matrix is when the number of rows is exactly equal to the number of columns. So a 2 by 2, or a 3 by 3, or a 4 by 4. Now, we're going to be using matrices to solve systems of equations in a few different ways, but one of them is to simply take a system of equations, a system of linear equations, and rewrite it as what we call an augmented matrix. And I actually like working with matrices when solving systems because it actually streamlines the process quite a bit so that I'm just focused on the coefficients. So this augmented matrix is going to look like the following. I'm going to take just the coefficients from my first row. So 1, 3, 4, and I just took 1, 3, and 4, right? Took those coefficients, and sometimes you'll see kind of these dots going down. I actually just like to use a line because it saves me time to separate the coefficients from the solution column, which would be 7. So if I want to finish this augmented matrix, I would write this as 2, 7, 5, and 10, 3, 10, 4, and 27. Right? So that's how we take a system of equations and write it as what we call an augmented matrix. Now, something that we're going to discuss today is the process of taking a system that's written as an augmented matrix, or even if it's not written in matrix form, if we just take a system and we write it first off in row echelon form, or REF, as we discussed in our previous videos. And then we continue on to have zeros everywhere else. So we're also going to have zeros here as well, so that we just have ones down the main diagonal. And this is what's known as reduced row echelon form. It's like row echelon form to the next level. And this process was developed by someone named Wilhelm Jordan, and he just continued on with the Gaussian elimination that Carl Friedrich Gauss first developed. So what is the benefit of taking a system and putting it in reduced row echelon form, or RREF? Well, once you have zeros everywhere else except for the main diagonal and you have ones in there, then what we can pretty much identify is that whatever value here is your z value. Whatever value is here is what y is equal to, and so on. This value would be what x is. It essentially prevents us from, or stops us from having to do back substitution. Okay, now as we do our Gauss-Jordan elimination, so students often will ask me, Mr. No, is there a method, or I should say an order in which you want me to eliminate these terms? And while it doesn't have to work in the specific order, I often find that it is helpful for students to first do the Gaussian elimination. In other words, get zeros as coefficients there. and then do the Jordan part of that, which is to kind of move in this counterclockwise order. So I would really just kind of show something like this is Gauss, and then doing this part here, eliminating those coefficients is the Jordan. So you're kind of moving counterclockwise to do the Gauss-Jordan elimination. Now, do you have to do it in this order? No, but I find that it's a lot easier, honestly, if you do. So I want to do one example of Gauss-Jordan elimination with this system written as an augmented matrix. So I believe we went ahead and did that. So I'm just going to copy and paste that over here. So there's my system written as an augmented matrix. So now I'm going to do the same series of row operations that I did previously. So I like my first row the way it is. It says 1, 3, 4. I'm not going to touch that just yet because I've got a leading coefficient of 1 and I've got all three variables there. So I'm going to leave that alone as it is. But what I do want to do is I want to eliminate this +2 and this +3. So I'm going to use row 1 to do that. So I'm going to go -2 times row 1 plus row 2. And so this should give me 0, 1, -3, and then this should be -4. Next, I want to use row 1 again, this time multiplying it by -3, so that when I add it to row 3, I can eliminate that +3 term. So that should give me 0, 1, I believe that's -8, and then 6. So again, remember, I'm writing the row operation and I'm writing the result of that row operation right next to it. So I've just gotten rid of the 2 and 3. I've eliminated it. So I next want to move on to eliminating this 1. So I'm going to bring everything down as it is. So again, 1, 3, 4, 7. And then hopefully you're seeing why working within a matrix might make our lives just a little bit easier here, just so we don't have to write the operations or the variables every single time. So to eliminate this 1 value here in row 3, I can just simply subtract it from row 2. Or I could just say, for example, -1 times row 2 plus row 3. That's another way of doing it. It doesn't really matter. We're still going to eliminate that 0 there. So if I do it that way, I'm left with -5, and this should be +10. Now, I notice that I have a common factor of -5 in both of these, and ultimately I want this value to become 1 anyway. So I'm just going to go ahead and divide this whole row by -5. And I would write this as multiplying it by its reciprocal, -1/5. And so when I do that, this would just become +1, and this would become -2. So if I were just doing Gaussian elimination to get into REF, then I'd be done. But I want to continue this now, because now I want to move on to eliminating this -3 and this +4. Again, we're doing the Gaussian elimination, or Gauss-Jordan part of the elimination. So I'm going to go ahead and starting now from the bottom, because my bottom row is done. I'm done there. I've got everything that we need. So now if I want to eliminate that -3, I'm going to go 3 times row 3 plus row 2. And that would give me 0, 1, and 0. And this would give me -10. And then if I want to eliminate that +4 in row 1, I'm going to multiply row 3 by -4 and add it to row 1. So that would give me 1, 3, now that's 0, and now I've got a +8 plus a +7, so that would be 15. And we're pretty close. We're pretty close. We actually just need to now, the last thing we want to eliminate next is that 3. So I'm going to continue, I'm going to move everything over here. I'm going to write down what we have so far, 0, 0, 1, -2. Let's draw that line down the middle. 0, 1, 0, -10. So I've got the RREF in rows 2 and 3. So the only thing that's missing now is for me to eliminate that +3 in row 1. So I'm going to go -3 times row 2 plus row 1. And that should give me 1. That 3 gets eliminated, 0. And that should give me +45. So the Gauss-Jordan part of this is simply now not having to do any back substitution once we got it into REF, but just continuing on so that we have 1s down the main diagonal, 0s everywhere else. So we can establish that my z value is equal to -2, my y is -10, and my x is 45. And I'm going to write that as an ordered triple. So there would be my solution, written as an ordered triple. Now, I'm going to encourage you now to try the next problem on your own to do Gauss-Jordan elimination here. A bit of a spoiler alert, as you do this, you should actually find that this is a dependent system, in which case it is impossible for us to get this into RREF, in which case you would just let one of your variables be equal to a, some real number, and express your solution for this dependent system. So go ahead and check your solutions with what I have uploaded to the classroom page, and hopefully this helps give you some understanding as to what Gauss-Jordan elimination is.